Hello, Math 10a. I'm going to be talking today about section 3.9 on derivatives of exponential and log functions. This is going to round out our toolbox of derivative formulas. At the end of the section, we'll be able to take derivatives of basically any function you could write down in terms of arithmetic, trig functions, exponentials, logs, you name it. It's really an incredible thing to be able to do. You should not take it for granted. Now, what I'm going to start with is probably the most infamous function of modern times, the exponential. And as several of these videos have before, I'll be starting with COVID graphs. So what I have here is the Johns Hopkins University page, and this is on the Wayback Machine from late March. Not a time I like to think about very much, but the illustrative value here was too good to pass up. So this is the graph of confirmed cases at the time. You can see it's going up with no end in sight at the moment. And we can click over to the other tab here, which is the daily increase. And it's also going up alarmingly fast. But one thing I noticed, and noticed at the time, was that if you look at the shape of these two graphs, they look almost identical. And well, what is daily increase but the rate of change of confirmed cases over time? This graph is the derivative of this graph. And so we have the sort of curious instance of a function which is almost equal to its own derivative. Now, not quite equal if you're paying attention. Paying very close attention, you might see that the labels over on this graph, the y-axis goes up to 700,000, and on this graph goes up to 70,000. So the scale is about 10 times less on this graph as opposed to the first one here. But we at least have a function whose derivative is proportional to its current value. And we also have this logarithmic graph. We'll be talking about logarithms later too. So logarithmic graphs are an important thing to think about. But this is the defining property of exponential growth. It's when you have the rate of change of a function proportional to, this sign here means proportional to, its current value. So in symbols, we might write that f prime of t, our derivative, equals k, some proportionality constant, times our current value. So this equation really captures what is meant by exponential growth. The more of a thing you have, the more it will be growing. And we'll see that this is satisfied by equations we think of as exponential equations. So, for instance, if we look at 2 to the x, the derivative of that will be natural log of 2 times 2 to the x. So this would be our k value in this equation. And more generally, the derivative of a to the x is going to be the natural log of a times a to the x. And this means that the derivative of e to the x, e being the base of the natural log, that's just going to be e to the x itself. And this is a really crucial formula. This is kind of the most basic one of all of these. And it really captures the idea of why e is such an interesting number in the first place. In your pre-calc class, you probably, if you were dealing with e, you saw it as some limit, or maybe didn't even define it precisely, because the real heart of the way e is defined is with calculus. It is the number such that, raising it to the power x, it is its own derivative. That's really the defining property of e, and is really quite a special thing for a function to be its own derivative. Now, of course, exponentials come up in the real world all the time, in virus growth, growth of other populations. The more, contagious people you have around, the more the virus will spread that day. It comes up in compound interest. The more money you have in the bank, the more money you'll make in interest. It comes up in radioactive decay. Say you've got a hunk of uranium on your desk. You should be careful that it's less than 100 pounds, otherwise it might go critical. But if you've got a hunk of uranium on your desk, each atom in that uranium has a equal chance of decaying at any given second. So the amount of decay you have will be proportional to the total amount of uranium on your desk. And this time, actually, the change is negative. You're getting less of it over time. And if you wait, say, 700 million years, then come back to your desk, you'll see you have half as much uranium as before. And then 700 million years after that, you'll have half again as much as you had before, no matter how much you started with. So this fixed half-life property is another exponential property, just that the decay, the growth is negative, so it's exponential decay. And these are some of the classic examples of exponential functions. Now, just as you undo multiplication with division, you undo addition with subtraction, you undo powers with roots, you undo exponentials with logs. So while we're here, we might as well look at the derivatives of log functions. So you should remember the graph of a log function looks like this. It looks like the graph of an exponential, flipped around the line y equals x, because that is a property of inverse functions. And we'll see, what should the derivative of log look like? Well, we see it's always increasing, and over here by 0, it looks like it has maybe an almost infinite slope. So it'll be coming down from infinity, and then it sort of flattens out. And if it continued on here, we'd see it just gets flatter and flatter. So we kind of come down and then approach 0. And maybe this would look familiar. And we'll see, in fact, that the derivative of log base 2 of x is 1 over natural log of 2 times x. So some proportionality constant times 1 over x. And I shouldn't have said proportionality, just some constant. The derivative of the natural log of x turns out to be exactly 1 over x itself. So another very important formula, and logarithms come up all the time in science as well. They're used in labeling graphs in a lot of applications. We perceive things logarithmically, musical pitch, intensity of light and sound. So logarithms are very important in applications as well as being mathematically interesting in their own right. And one final thing. I told you at the beginning of this video that by the end of the section, we'll be able to take the derivative of basically any function you can write down. And you might think that we're at that point now, but there's still a slight wrinkle, which is, what if we have a function like f of x equals x to the power of x? Now, we can't use the power rule, because the power rule, right, would be x to the n. We'd need n to be constant. And we can't use the rule from above about derivative of a to the x, because we need this a to be constant. In this example, neither is constant. Either the base nor the exponent is constant. So we can't use any of the rules we've come up with so far. The way we'll get around this is with a clever trick using logs called logarithmic differentiation, which is basically a twist on implicit differentiation. And once we've done that, then we will have completed our toolbox of ways to take derivatives, and we'll move on to learning about a whole bunch of different ways to apply derivatives and what else they're good for. So I'll leave you there. Thanks for watching, and have a good day.